In the last video, we demonstrated how we could use these two cables in close proximity to make a capacitor. Obviously, it wasn't a capacitor you would ever use in a circuit. Number one, I mean, come on, it's just two cables, and every time they move, the capacitance changes. But even so, if it was done ideally and you didn't care about the fact that it was enormous and had very little capacitance and all of the other reasons why you would never use it, the fact that it was not only functioning as a capacitor, but the fact that it was so long that it would also make a remarkably good antenna would also be a cause for concern, right? So the fact that you have this long open-ended cable or two open-ended cables in the circuit would also make it an antenna. This would not be a good capacitor, right? So it was just a functional example. It wouldn't be very adjustable either, right? So you would have something like this, and this is one that I pulled out of my collection. This is an open air capacitor from an Atwater Kent, and you could see that the bars on the bottom are all tied together and they're stationary. They don't move. You know, these other bars are also on top tied together, but they're not stationary. And by turning this knob, I just calibrated this one really nicely. By turning this knob, we can have the top bars intertwine with the bottom bars, but never actually touch. You know, if I get the camera just right, you can see they get as close as possible. They don't touch. They sort of sandwich each other, and by doing so, we end up with the same effect, which is to have basically two sides with a lot of surface area that get as close as possible without touching, so the electrons can collect on one side and condense, if you would. And because it's adjustable, because we can move it in and out and control the amount of surface area that intertwines, we have an adjustable capacitor. And this is in fact an adjustable capacitor from an Atwater Kent radio, a Model 20. And this is one that I use for some purposes as need be, right? So the bottom portion is connected. You can see the metal bar comes off to this screw right over here, and then the top portion is connected to that screw right over here. So there's our two ends. They never actually touch each other, and you have a tuning capacitor, right? So you connect that to a coil, and then it tunes. So if we were to hook this device, just trying to focus on here, if we were to hook this device up to this unit, we would be able to take some pretty specific measurements. There's a notch up here. I realize that the paint is worked itself away, but if I were to start at 0, I'd be able to hook it up to this device and take some pretty specific measurements. I've done so already, and you could see that already accounting for 3 picofarads in the cable just sitting there doing nothing. There are some capacitances within the unit itself, and that's because, you know, even not intertwined, you could see that the bottom and top do sit within the proximity to each other, right? And because of this, there is some capacitance there, right? And that accounts for, at 0, at the furthest position where there's no interlocking whatsoever, we end up with 19 picofarads of capacitance. And then I did 20, 40, and I did 50 just right at the halfway point, 60, 80, and 100. So the spread that we really get is 19 picofarads at the 0 position, 178 at the 50 position, and 296 at the 100 position. And obviously then just subtract 3 from those values. So you got 0, 50, and 100 being the tuning knob, and those are the 3 values that we've derived with a high degree of accuracy from this unit, so we know what those values are. So if we could then take this capacitor and marry it to a coil, we can actually control where that coil will resonate in an LC circuit. I've also pulled this coil again, or possibly another coil. I've got several of these out of my bin. This is an Atwater Kent coil of the same vintage as the this capacitor here, and I've put it up here on the Genrad to show us that this coil is reading 0.304. It looks like 0.304 microhenries right there. And I've annotated that on the paper here. Its reason will become relevant shortly. So we have this coil, and the coil, although this particular coil has taps on it, for the purpose of one end to the other, that is our reading. I said microhenries, I meant millihenries is what I meant to say, right? So MH, I correct myself. So this coil, non-adjustable, 304. I wrote down the Q, but this Q is for 1,000 hertz. Obviously the Q has almost no function in what we're doing, but I figured why not. And the adjustable portion of this circuit is 19 picofarads to a maximum of 296 picofarads. So that's two of the variables that we currently have in play right now, as read on the Genrad. Now, given this coil here is a constant, if I were to set this capacitor here to 0 in the 0 position, which we said is the lowest amount of capacitance, which is 19 picofarads, which I put up the top here, then our two values would be, for capacitance would be 19 picofarads, and for the inductance would be 0.304 millihenries. There is an equation we could use that if we were to tie these two together, what the resonant frequency would be, right? And that's frequency equals 1 over 2 pi times the square root of the inductance times capacitance, as seen here. And what I did is I broke out the math in the long form so you could see that. And we could see that the inductance is 0.000304, right? Because it's 0.304 millihenries. And the capacitance is really low. You could see that it's out to the 12th there. It's 19 picofarads. And when I multiply them together, I get LC. And then that LC I get the square root of to get the 0.00000076 multiplied by 2 pi, which gives me 0.000000477728. And then with that value, we look again at our equation. Frequency equals 1 over 2 pi times the square root of LC. So I get 1 over that value and end up with 2,095,000 hertz. And to make it more readable, we end up with 2,095 kilohertz. So now I'm going to take the maximum value, which is the 296 picofarads, and plug it in to the very same equation and see what we end up with for the maximum value. So we'll end up with the outer frequencies that'll be possible by turning this knob to 0 and to 100. By tuning the capacitor all the way to 100 or maximum capacitance, we end up with 296 picofarads. And by plugging that into the very same equation with our new values, we end up with a resonant frequency of 530 kilohertz. If we look at these two frequencies for the minimum and maximum, 530 kilohertz and 2095 kilohertz, we could see that the combination of this capacitor and coil is designed to fit within the AM broadcast band. In this instance, long before it was commonplace to have frequencies written on the actual tuning dials, 100 would have been the lower frequency at around 540 kilohertz, the bottom of the AM band. And as you would turn it down, it would logically it would be sort of inverse, but the frequency would go up. We would find that on this knob, probably around 10 or 15 on this knob would have been the top at around 1600 kilohertz, which would have been the top of the band. 0 would have been actually beyond the spectrum itself. It would have been outside of the AM broadcast band. So between 0 and 10 probably would have been nothing. But this is how the tuning knob would have worked to get you whatever frequency you wanted on the AM band back then. On the TFR radios, there would have been 3 separate knobs in order to tune in a particular radio frequency back then, not just one. So it occurred to me yesterday that since this was an Atwater Kent capacitor and coil, that it might in fact mount onto the back of this, which it did. I doubt it was from the same radio, or it could have been from the same radio. Either way, it mounted on there, and I went and soldered on the ends to here. So we have an LC tank circuit right here, all done. And this happens to be a coil that had the taps on it, right? So we're not using those. But I've got this all together as one, right? So we have a resonant, adjustable resonant circuit right here. Unfortunately, by doing this, there are slight changes to the capacitance and slight changes to the inductance, obviously, because we got them connected now. So I have to remeasure those values on the Genrad. And obviously in doing so, I'm going to have to remeasure the values for what the resonant frequencies are for 0 and 100 and everything in between. I'm not going to do the math by hand. It's just ridiculous. I'm going to use, obviously, a program that I'm just going to type them in and get those values. And then I'm going to record them all onto paper and get that all out of the way beforehand. Turns out I was reading the Genrad wrong last time. This is not 304. This is 319. I was writing 304. The math was right. The results were wrong, but they weren't far off. I did remeasure everything on this. This is all correct, and all the numbers were the same. But this was 319, and that's cool because I did everything with the computer, and all it did was make it wider. So everything still fits to what I had said earlier, except that it works between 517 and 2044. There was no significant change to the coil or the capacitor as a result of merging the two together. These are the final values that were recorded from the computer. Just showing the dial position. This is just the number on the dial from 0 to 100 in 20s with obviously just the 50 in the middle. The picofarads for those values and the resulting mathematical equation between the microhenries and the capacitance together. So this is the resonant frequency according to the mathematical equations from 518 kilohertz up to 2044 kilohertz. That's all this is. Nothing else is filled out, right? What I've got here on this side is my signal generator, function generator, my oscilloscope, and this tank circuit that we've been working on. And what I have, I'll talk through this. It looks a little bit messy, you know. I'm trying to get this going here as good as possible. I went and touched it. I've detuned it. What I have is the connection is coming off of here, and it's connected in parallel to the tank circuit, except for the fact that it's not directly connected. I have it going through a 90K resistor. And the reason is so I could drive this, but end up with an extremely low signal. I want a very weak signal going in here, so I don't saturate this. I want this on very low. You can see I have it 500 millivolts per division, right? Everything else, the other side of this, as well as the oscilloscope, is connected directly to it in parallel, right? And what I've set up, at least right now, is I just moved it, but the dial's in and around 100. And I've set up a sweep generator that goes from 0 to 1,000. So we can just get a quick look on the oscilloscope what happens when I start the sweep. And this is basically going to go from 0 to 1,000 over the course of 30 seconds. And you're going to see what happens to the signal is going to peak when it becomes resonant and jump back down. So I'm going to hit the sweep button here and hit start, and you're going to watch what happens, right? So the sweep generator is starting, and you can watch at least down here the frequency. And as it approaches the lower 500s, the signal peaks and jumps back down, and it's going to continue to drop as it leaves resonance. And that's going to work its way to 1,000, and the sweep generator just sort of keeps going till it hits 1,000, and then it starts all over again, because that's what sweep generators do, and the process sort of repeats itself. And this kind of brings me into the ballpark, you know, and I kind of try to set this thing for 100 to at least try and keep it on par with this. And then what I do is I sort of hand walk it once I get there to find out at what point this thing actually peaked, to see how close we are, and then kind of do that with all of these, and then sort of work my way further down this testing event. It's also possible to look at this under an FFT like this. A little hard to see here, but you can see there it is, and as it approaches around 500 kilohertz, you can see it's starting to peak. I put some cursor lines there so you could see it peak right there. According to the cursor measurements, from the beginning it's an increase of about 30.4 dB, so, which seems kind of strange because as it works its way down it never goes that low again. But FFT, it's at least interesting to look. This is definitely not a spectrum analyzer by any means, but it's better than nothing. I went and checked the knob and made sure it was exactly 100 before I did this test, to make sure I wasn't wasting my time. And then I went onto the oscilloscope and checked the volts per division knob and set it all the way down to 50 millivolts per division. Made it extremely sensitive and used a position to set up a point of reference. And the reason why I did that is I wanted to dial in the kilohertz down to 1 kilohertz. I didn't want to go nuts, right? But I wanted to see the exact point at which the frequency peaked, and then compare it to the math. And I know there's going to be some changes and variance going on and what have you. I know the math is not going to be perfect, but I want to see how close I got. And what I ended up with, the exact point at which it peaked and sloped on each side, it sloped on 519 and 521, which gave me a peak of 520 kilohertz. And the math showed, believe it or not, 518, so it was only off by 2 kilohertz, which was pretty close. And it's also something to be said about all the wires and stuff that are also in place here changes these values as well, remember, you know. So we are adding some capacitance here, so it is possible that with extra capacitance being added, that we extra value. I don't want to speak in terms of capacitance, but we are adding some extra values into this circuit, causing a slight shift. But to get that close with these values is pretty cool. I'm going to go through the other ones and see what we arrive at, how close we get to these values. Because being off by 2 is really nice. Let's see if we can make our way all the way up to the 0 knob of the dial. That being said, it's also worth pointing out that this particular dial, you know, I could have had it off by a hair because there's no really good point of reference for 100. You know, turning the knob and then turning it back to 100 could have also been off. It could in fact be on 520 right now and not 518. So that too, you know, all things being lined up here, building this tank circuit and getting it this close shows that this is close enough to be on the money as far as I'm concerned. So that's pretty cool. Call that a success. So here's what the results ended up being. 100, which is what the knob was actually calibrated to when it was first set up, ended up being +2, wasn't off by very much. My idea was that in setting that up, the knob very well could have been adjusted for or rotated to accommodate pretty much the rest of everything by shifting the knob itself, you know, the values on the front. If the values on the front had frequency as opposed to these numbers, then loosening the knob and moving them could have aligned the knob. You could see they're all off by, you know, +14 in and around. Some of the newer type knobs actually had areas where you could actually bend some of the metal plates to change the capacitances in between them to accommodate for that. And you could see that happen pretty much in and around here, all the way to the last two. On the last two, you watch a very sharp drop off, and all of a sudden, and it is a sharp drop off, because on the third one you still have you have +14, and all of a sudden it drops down a little bit to +8, and then drops to -20, which is substantial, you know, when you think about it, right? And then to -634. And I think what we're seeing here is as we get to the end, what we're having is remember, these minuses are just a comparison between these math results. They don't have any numerical value. The important thing to look at is once again, I found I'm getting ahead of myself. with the coil being constant and the capacitor being variable, we found that given a constant frequency, we could find out with a great deal of accuracy exactly what the capacitance is. And this is because we can't actually measure the capacitance while it's connected to the coil, because we end up with a dead short, right? But we can measure what the capacitance is with regard to the formula for the for this LC circuit as a whole, right? And I did that, and what I found was this, basically, is they're actually not very far off. It's off by a couple of picofarads here and there. And basically what that means is that this knob could have been turned a little bit in this direction and a little bit in that direction. And what I found for the very bottom one is due to the shape of the way this is, the end of the metal splines here, it sort of has a teardrop shape to it, and it's very hard to show by looking at it, but it causes a really big roll off at the end. And just by being off one notch, that 19 could have been 40, could have been 60. So it's very hard to tell, right? So we're just gonna not worry about what 0 was, right? And say that, you know, all is fair. So basically we've derived that. But what else I wanted to look at was what would happen if we left it. I picked a frequency right in the middle, 681, and I just picked that because that was what it turned out to be for 50%, right, on the dial. To have that number appear, and then I dialed it in to look at the knob, and then say what happens if we leave the frequency alone and then just use the knob to tune the frequency, right? So if I tune away from 50, you know, down that way, it goes away, and then I bring it back to 50, and then I tune away from 50 again, you know, we go away from 50, right? So obviously, if I peak it up, you know, we can see exactly where the resonant frequency is. And there are more effective ways to do this with regard to measurement. I mean, we see this visually, but using the FFT, we could actually see how many decibels of power or decibels measured to see what the roll-off is. So I've adjusted my FFT for viewability through my camera. And what I've done is I've added some cursors that show a change in decibels from start to end cursors right here. And I've already set this up so you can see what happens when I adjust the tuner. And when I adjust the tuner, you can see I've marked or captured the highest and lowest points, right? So I'm going to turn it out of tune, and it goes all the way down. And it's somewhat different. If I take my hand all the way away, it'll drop a little bit lower. And now it won't because I'm recording. But if I turn it all the way up and tune it to its peak, that's about as high as it goes, and then you can see that's about as low as it goes. And in looking at that, we can do the math, or it does the math for me conveniently, and we can see that the difference in magnitude is 14.6 decibels based on the minimum and maximum amount of voltage or power, or depending on how you want to look at this with regard to how this FFT is looking at this waveform. So if we were to look at it in the time domain, you know, we would look at it and we would see it like this, you know, and come back down. That's just sort of a measurement of amplitude, you know. But here we could look at it in decibels a bit more logarithmically, a lot more logarithmically, and see that. What I cannot do with this is see it over the spread of how far, right? So I can't tell you like what the Q is, what the filtering. I don't have a this function generator is kind of crappy, and it doesn't have a signal for triggering, right? So I mean the oscilloscope has an input for triggering, right? You would think with a sweep generator that this would have some sort of trigger, right? And basically, for those who don't know, is that I could go over a certain area, like we're at 681, so I could go like from 600 or 500 to 700, and between very quickly from 500 to 700 every time, just trigger that on the oscilloscope to make the oscilloscope just take a picture of that very quick moment. and that would draw a picture for me that could show me what the properties of this was, right? That'd be fantastic. But this piece of crap doesn't even do that. It's absolutely amazing. So unfortunately, because I don't have that signal that comes out of this unit, I can't do that, you know. And I can, you know, at least I got this, you know, so I could, my oscilloscope is able to do this much, and obviously the oscilloscope would be able to do much more if the function generator were able to do that task, and it can't. But we were able to see that, at least, you know, as far as magnitude goes, the decibel increase from not being tuned to being perfectly tuned. Another problem with magnitude becomes resolution. If I change the settings and look at it like this, if I look at beginning and end and watch as I turn it up and down, we can see that the change in decibels is listed as 4.8 in doing it like this. And this tells me that using the FFT in this regard is a poor choice, at least in this setting, to see what our minimum and maximum is for this. And this may be the wrong way in going about doing this. So ideally, what I would want is something like this that triggers up. That would really be all we needed, is the ability to trigger and not use the FFT at all. What we'd be seeing is just that one snapshot where it was triggered. So we'd be seeing basically the bandwidth over that setting. So we would see the start and the end of the frequency, and then we'd watch the amplitude increase and decrease from the beginning to the end of that sweep, which would show us the characteristic. And that's something that unfortunately I can't replicate in this video. I hope to find another way of going about doing this that isn't so cumbersome that it's just not worth showing, or find a good way to get a sweep generator going here so I can do that. Either way, this kind of ends what we're trying to do right now, which is to get this tank circuit going, and we did. So we were able to achieve resonance, and more importantly, or at least somewhat important, we're able to also say that given a constant frequency and a constant inductance, we can now, with great accuracy, almost matching, or in some ways matching this, find out the capacitance of a capacitor. And this is really useful when you consider that the impedance bridge is not capable of reading capacitance in a tank circuit like this, unless it was a series tank circuit, right? Because if it was in series, there wouldn't be a short. But in parallel like this, you can't read the capacitance, right? But you can read it like this, and it's reading all the capacitances. It's reading the wires and the cables and everything all together here, obviously. But you have the ability to do so, and that's what's demonstrated here by peaking it and finding out, you know, where it peaked, what that capacitance is. So pretty cool. So that's my demonstration on putting together this tank circuit and everything, and finding out all this wonderful stuff through math. Thanks for watching.